Hello, welcome to the second video covering the chapter on engines and refrigerators, chapter 21. So this video is going to continue on with the discussion, and in particular focus on not just the general energy principles of engines and refrigerators, but particularly looking at particular cycles in a PV plane. So these are ideal gases where the volume can change. And we want to be able to calculate, given any cycle, any closed path in a PV diagram, what is the efficiency if it's an engine or the coefficient of performance if it's a fridge. So really, this whole video is going to be looking at two examples. It's going to be this one picture, one time where we're going to go this way. So thinking about going this way, this way, this way, this way around the cycle. That's the case if it's a engine, and then the opposite way if it's a fridge, actually. Okay, so first a couple definitions. So a cycle in a PV diagram is a closed path. So I've already mentioned this term, closed path in a PV diagram. Closed path on a PV diagram. So if the cycle is PV, if your cycle is going this way, so notice how the arrows are indicating that we're going around in the clockwise direction, and this is an engine. And if we're going around this way, this is going to be a fridge. So for the reason for that is if you take a look at the area right here. So overall, in one whole cycle, work is being done by the gas. So if you look at maybe point A to point B right here, work is being done by the gas. A lot of work is being done by the gas, the area underneath there, and then the work done by the gas in this returning path from B to A is negative. But it's not as big in magnitude. So overall, the overall work done by the system, by the gas, is positive in one cycle. And remember, if the system is doing work, that's exactly what we want out of an engine. So the overall effect here is that the work done by the system is positive, and the overall heat delivered to the gas was positive. That's why we're going back to the same original thermal energy. So the overall effect of these, so Q overall in one whole cycle is added to the gas, is added to the system, and it does work, and the system does work. And W out is positive. Okay, so in one whole cycle, delta E thermal is 0. So it's Q added to the gas minus the work done by the gas, the net work done by the gas. So adding up all the steps in the cycle. So this is a positive number minus a positive number, and then you get back to your original point, 0. So this is exactly what an engine is, right? You give the system heat, and it does work. And that's exactly what we want right there. For a fridge, overall Q is taken out of the system. So in a fridge, maybe the way to think of it is first in terms of work. So let's first look at so because this is operating in reverse, it's not work done by the system, but overall work is done on the system. Overall work is done on the system. So maybe Wn would be the overall work that the outside, that the surroundings are doing on the system. And again, looking at the first law of thermodynamics, W or delta E thermal, which is Q plus Wn. So this is going to be the net work on. I'm writing it this way because overall this is the positive quantity right there. So it appears that if we go back to our original point, the delta E has to be 0 because E thermal is a state function. So it looks like the overall heat left the gas. So heat leaves the system. Okay, so really this is really what's going on is that the low temperature reservoir is heating up the system, and then you're also doing work on the system, and then more energy in the form of heat is leaving the system than what entered. Right, just like that energy flow diagram depicted in the previous video. Okay, so let's start to tackle part A of this problem, and think about what steps do we need to what do we need to look at to find out what the thermal efficiency is. So for part A, if we're going to look at that cycle and say that we have an engine, then we definitely know the order that the steps are going here. It's definitely going in this direction so that there's oops, it's the opposite way. Sorry. So an engine will go around this way, because remember, we want the overall area underneath. So when you add up all the 4 steps, the overall area needs to be positive. The overall work done by the gas is positive. So this is the engine. So just because of the direction of the arrows, this is an engine. Okay, so we're given a particular engine by being told exactly what the maximum and minimum pressures and volumes were. Okay, so the thing to think about in all of these diagrams is when is heat being delivered to the system? So if you think back on this diagram, remember the cold temperature reservoir and the hot reservoir, and the point of an engine is this step is QH, this is Q cold, and we're getting work out of this. And in the formula for efficiency, it's the overall work output divided by QH. So looking at these in more detail, this is the net work done by the gas. So in other words, it's going to be the area right here. And notice how you have to take into account all steps here, like all 4 steps in this cycle are relevant. 2 of them happen to be 0 because they happen to be vertical lines, but you would have to add up all 4 W bys. So in this case, for this example, W out, the output is the area right there, is positive, is looks like base times height is P naught V naught. That's the overall work output. So that's what this value is going to be what we plug into the numerator right here. Now for the denominator, this is a little bit tougher. So for QH, what you do is you look at, this is anytime energy in the form of, you have to add up all the heats that flow into the system. So anytime the system is heated up, anytime Q is positive. So you have to look at all 4 of these steps. Maybe I should choose a different color for this part. We have to look at all 4 of these steps. So say 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. You have to think about which steps is Q positive, which steps is heat added to the gas. So maybe before that, for which steps is Q positive? Well, 1 to 2, we're definitely heating up the gas, right? Energy went from the surroundings to the gas, which is exactly what's depicted right here. So Q1 to 2, Q1, 2 is positive. And it looks like Q2, 3 is positive as well. And then steps 3, 4, and 4, 1 are where Q is negative for the system. Those steps are involved in the energy in the form of heat leaving the system going towards the surroundings. So that would go towards QC. So just for completeness, I'll put 3, 4 is negative, Q41 is also negative. But these two are the ones that are relevant for QH. So these two steps, these are the steps where heat, energy in the form of heat, flows into the system. So therefore, QH is going to be equal to Q12 plus Q23. Okay, so what is Q12 and Q23? So Q12, so remember, heat in either an isobaric or an isochoric process is going to be NC delta T. So really, to answer this question, we have to know the kind of gas that we have in order to say what CV is. So let's just say that we have a monoatomic gas. So we have to say that in this original diagram, we started with a monoatomic gas. If you have a diatomic gas where the rotational modes are activated, then you'll get a different efficiency. Okay, so assuming we have a monoatomic gas, we can go ahead and plug in CV is 3/2 R. So this is 3/2 NR delta T. And I'm going to write this in a way so that I have delta nRT. So N and R are constants. I can put them inside this triangle, inside this delta. And this is nice because nRT is equal to PV. So this is change in P times V. So Q12 is equal to 3/2, and then delta PV is P final V final minus P initial V initial. So it looks like P final and V final for that step 1 to 2. It looks like that product has doubled. So it looks like this is 3/2. The final pressure was 2 P naught. The final volume is still V naught, and then minus P naught V naught. So it looks like this is 3 P naught V naught. Okay, similarly, when you do Q23, this is NCP delta T because it's an isobaric process. CP will be, instead of 3/2, it'll be 5/2. This will be delta nRT. But remember, this is delta PV. So this is 5/2 times, now P final there is 2 P naught, V final is 2 V naught minus 2 P naught V naught. Those are the initial values. So it's 4 minus 2 is 2. Looks like this is 5. Oops, I made a mistake right here, right? 2 minus 1 is 1 times 3/2 is 3/2. But this one, there is a factor of 2 in the square brackets, so you get 5 P naught V naught. Okay, so both of these pieces need to add together to give us QH. So maybe going back now to QH. QH are all the Q's that are positive. So it looks like so in this problem, it's 1, 2 plus 2, 3 is 5 plus 3/2 is 13/2. Oops. P naught V naught. Okay, so finally, putting all this together, eta, the efficiency of the engine, which is the net work output divided by the net heat that flowed into the system, is P naught V naught over 13/2 P naught V naught. Looks like it's 2/13. Okay, so not terribly efficient, between 10 and 20% efficiency, which is not good. So your book sums this up, a strategy for heat engine problems. Draw the PV diagram if they didn't give it to you already. So really they're telling you to do Q, W, and delta E for each process. That's a little bit of overkill. Really all you need are the Q's that contribute to QH. And it's this step right here, add just the positive values of Q to find QH. That's generally the hardest part of all this. But that's definitely a relevant piece because that goes directly into the calculation for efficiency. And then for the net work done by the gas in one cycle. It's just the area bounded between here. So that W out is going to be the area here. So if you had more complicated shapes, that takes a little bit more work. Like if you had an isothermal, it will involve a nRT log, the final over the initial, but you can imagine how this would generalize. Okay, good. So, they tell you to do a little bit more work as a double check to make sure that delta E is 0. But as long as you did each step correctly, you wouldn't have to do that many steps. Okay, that's just doing a little bit more work to double check your answer. Okay, so now let's pretend we had a fridge. And the fridge is very similar to the engine we just did in that it's the same path on a PV diagram. So really this should go, that's maybe a little bit closer to P naught and 2 P naught. So again, we're going to assume we have a monoatomic gas. But now instead of going this way, instead of going that way around the cycle, we're going to go the opposite way. And now all of a sudden it becomes a fridge. So if you go around this way, overall, the work done by the gas is negative, which means work is being done on the gas overall. So now this is a fridge, just because of the direction of the arrows. And again, we're going to assume we have a monoatomic gas, so we can actually calculate Q values. Okay, so the work, so this area, if you add up all of the W bys, you'll get a negative quantity. But the overall work input is, so if you add the work done on the gas for each of the steps, the magnitude is equal to the work done by the gas. You just always have to flip the sign. So basically, if we just take the area there, so the area underneath there is technically negative, right? Because this piece is negative and then this piece is positive. So when you add them up, you get a negative quantity. So for a fridge, the area enclosed by the cycle is always negative. If you always just make that positive, so just whatever number you get, force it to be positive. So that's where these absolute value signs come in. That's the work that went into the system, into the gas. So here, this work is again going to be P naught V naught. Again, it's just the area forced to be positive. Okay, and that's perfect for this definition of coefficient of performance. So remember this is what we want, which is heat extracted from the cold temperature reservoir divided by what we had to pay for it. So for coefficient of performance, this denominator part is pretty easy because you can just read it off the graph. In the case where you have, in the case where you can read off the area pretty quickly. Again, if you have isotherms or adiabats, you have to actually do these integrals, and it becomes a little bit more complicated. Now for QC, so again, I want to draw this energy transfer diagram because it helps us think about what energies are relevant here. So again, this is the system. This is the cold, this is the hot. Now for a fridge, the energy flow is different than for a engine. So the cold temperature reservoir has heat flowing in. So QC, it's from the cold temperature reservoir, but it's going into the system. So the system's a little even colder than the cold temperature reservoir during these steps, during any step where Q is positive. And then overall, we're going to add energy in the form of work, and then the heat expelled to the high temperature reservoir is going to be the sum of those two from conservation of energy. So QC is going to be, we're going to add all Q's for all steps where Q is positive. Right? See how QC, this is where heat is flowing into our system. So our system right here, remember Q is positive anytime heat flows into the system. And that's the part we care about. That's the numerator right here on the coefficient of performance. So here, so now I have to number these a little bit differently. I can't do number 2 up here. Right now I wanted to follow the order 1, 2, 3, 4 in the steps that the gas is going through the cycle. Oops, 1, 2, 3, 4. So it looks like Q is positive for this step, 1, 2, and 3, 4 in that step. So here, in this problem, QC is equal to Q12 plus Q23. But remember, those numbers are labeled differently than when we were doing the engine case. So it's again when the Q's are positive, but it's a very different interpretation. These are at the lower temperature. This is heat flowing in from the cold temperature reservoir. So again, so the steps involved here, because the paths are isochoric and isobaric, it's going to be a similar type of computation as what we did before. So here Q12 would be NCP delta T. So this is 5/2 R delta PV. Oops, bring the R in to right delta PV. So this would be 5/2. Looks like P final, V final is 2 P naught V naught, and then the initial one is P naught V naught. So this is 2 P naught V naught minus P naught V naught is 5/2 P naught V naught. And then Q23, it's similar, except remember it's isochoric, so it's going to be 3/2 delta PV. And this time we're going to 4, so 2 P naught times 2 V naught is going to be 4 P naught V naught minus 2 P naught V naught for the initial point. So this is going to be, I'll just write it out, 4 P naught V naught. It looks like this is 3. So we can plug this in to get the coefficient of performance of this ideal gas refrigerator. It's QC over the network input. So QC is going to be the sum of these two pieces. 5/2 plus 6/2 is 11/2 P naught V naught. And the network input, which was the magnitude of the area there, is P naught V naught. So it looks like this is 11/2. Remember, there's no restriction that the coefficient of performance has to be less than 1, like there is for engines. So your book does this for plugging in a bunch of numbers, whereas we did it more abstractly with P naught and V naught. So when they talk about refrigerators, again, they give a they didn't give a table like they did for this step, for the heat engine problems. But again, you might expect that you add the negative values for a fridge, but no, you still add the positive values of Q to find, except this time it's QC instead of QH. And that's exactly the thing that appears in our measure of performance, our coefficient of performance. Okay, so once you have this, then you can answer any auxiliary questions in your problem relating the work input to the net heat extracted. So basically, so what I'm saying is, once you have this number right here, this 11/2, then you can relate these two quantities. So if you had one of those two, you can find the other one. Yeah, so this is useful because we analyze it just for one cycle, but who knows, especially for an engine, who knows how many times it's running per minute? It could be thousands of times. So in terms of the actual magnitudes of these quantities, a lot of times that's a separate question than just analyzing one cycle of this to get the efficiency out. And then once you know the efficiency, then once you have one of these two numbers, you know the other one, which is pretty useful for seeing just how much work you can get out of an engine based on your input gasoline. Okay, so obviously I didn't do every type of problem because you could have to find heats or works area under the curve for different types of processes. Right? You could have adiabats or isotherms where this gets more complicated, but conceptually it's the same idea. You have to separate each step and figure out which Q's are positive, and you can ignore the other ones. So notice how like step 3, 4, and 4, 1, we totally disregarded when we were calculating the coefficient of performance here. And that was okay. It turns out that it doesn't appear in this expression right here. Okay, happy calculating.